So here we go. Definition of the logarithmic function, and this is from algebra. It says for x positive, b positive, b not equal to 0, y equals log base b of x is equivalent to b to the y equals x. The function log f of x equals log base b of x is the logarithmic function base b. Now, as a reminder of what the log is and what the relationship is, because we're going to need that, is that if I take a look from college algebra, domain and range, and if I were to look at the forward process would be b to the x, so that's your exponential function. The inverse function is log base b. So it's the inverse of the exponential function. And so it says log base b of x for x positive, and you're going to say, well, why is that the case? Now let's think about the exponential function, and we did a graph of the exponential function. And if you remember, he looks like this. His domain was all real numbers, and his range was 0 to infinity. So how does that fit in? Well, if I'm going from the domain to the range, and the exponential function is the guy who does it, that means all real numbers is in the domain, and 0 to infinity is in the range. So what the logarithm has to work with are only numbers between 0 and infinity. Now that's why they say whatever you're taking the logarithm of has to be a positive number, because that's the only thing that's in his world are positive numbers, not including 0. Okay, so exponential takes it over, logarithm brings it back. Domain and range. One of the biggies, and it's equation solving more than it is in terms of some of the things we're going to do with derivatives, is being able to write things from log notation to exponential, exponential to log. This is 99% of our world, is going from log to exponential notation. And if you remember, that's where you say a to the y is equal to the inside, a to the y is equal to x. Going to log notation for me is always trickier, and this is the reason why. If I look at the relationship between logarithms and logarithms and exponentials, here I go again, and those of you who have had me for college algebra has seen plenty of my circles. If I look at what happens with b to the x, and here we go again, what are the x's? Well, they're all real numbers, but they're also the exponent of that base. So these guys are exponents. So exponents. I pick a value, put it up where the exponent is, right? And then I raise b to that power. So this is exponents. I always call this is the result. And that's the result of raising b to that exponent power. So that when you think about going backwards, the logarithm picks up the result and takes it back to the exponents. That's why we always say that the log is an exponent. we have lost what a logarithm is primarily, and that is because of our calculators. Our calculators, we just put numbers in and press logarithm and a number pops out and we haven't a clue what it is, unless you take some chemistry. Chemistry, you work with logs quite a bit in chemistry. I took more physics than chemistry, so in physics you don't work with it quite as much. So that if I wanted to go from exponential to log, what in my mind I look at, I have log, I have a base, I have what I'm taking the logarithm of, and I have the result of taking that log. Well, if you think about it, the base is the base is the base is the base. So whatever the base is, it picks up a result and returns it to an exponent. That's why we say the logarithm is an exponent. So anytime I have to rewrite something as a logarithm, I have a base, I have the thing I'm taking the logarithm of, and I have the result. The base in this instance is A. Now I've got a 50-50 chance of placing the 3 and the 2.1 in the right place. The logarithm picks up the result, which is a 2.1, and takes it back to the exponent where it came from. Picks up the result of the logarithm and then takes it back to the exponent where it came from. So it should be the case that a cubed is equal to 2.1, and it does. Now, we don't have to do that very often, thank goodness. Going from exponential to log. We're most of the time going from log to exponential to solve equations. That's good news, because that can be done quickly. So if I want to go from log to exponential, this says that b raised to the 2 power is equal to 4. And you can tell me what's b?
2.
2. Can't be minus 2 because bases cannot be negative. Now, what's going to be the big gun for us is finding the domain. Because remember, domains help set up our number line. Right? So that I need to know what the domain of the logarithm is. Well, f of x equals the log of some, whatever we're taking the logarithm of is an argument. And we know that whatever we're taking the logarithm of has to be positive. Because I can't take the log of a negative number. By the way, the log of a negative number is imaginary, if you want to know essentially what a log of a negative number is. But it is imaginary. So that if I want to find what is the log of x minus 1, I know that the argument must be positive, or x minus 1 must be positive, or x must be greater than 1. That means when I take the derivative, set it equal to 0, set up my number line in this instance is going to start out and not include 1, and it's going to be 1 to infinity. So that when I put my critical numbers on, and then I search for max, mins, all that thing, it's only going to be between 1 and infinity. Now let's remind ourselves of what the logarithmic, and this should be the graph of the basic log function, not exponential, good old cut and paste, what a logarithmic function looks like. Well, if I wanted to graph just a simple function, y equals log base 2 of x, what we did in college algebra, we rewrote that as 2 to the y is equal to x. I don't have log base 2 on my calculator. Well, most of us don't have log base 2 on our calculator. Depends upon the calculator. log base 2 on our calculators. So as a result, this says that 2 to the x is equal to y. And then in our t-bar chart, oh, I'm sorry, 2 to y is equal to x. Yeah. Yeah. 2 to the y is equal to x. So that means 2 to the y is equal to x. I'm going to put in y, and I'm going to get out x's, because remember, that's the inverse of the exponential function. So put in y's, get out x's. And this, because it's written as an exponential, no, -2, -1, 0, 1, and 2, put in y's. This ends up being 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, 2 to the 2. This is 1/4, 1/2, 1, 2, and 4. This guy has a VA at x equal 0. Because the exponential has an HA at what? Has an HA where? There he is. Has an HA where? Exponential.
0.
Has an HA at?
0.
Give me the front part of that.
0, 0.
Y equals 0. It's a horizontal line. So it's the x-axis. And if you're doing the inverse, you are flipping x and y. So if indeed the exponential has an HA at y equals 0, the logarithm will have a VA at x equals 0, because you're flipping x and y.
So it's always like that?
Always like that. Unless you have a translational shift, this guy has a VA at x equal 1, because he starts at 1. That's a shift to the right by 1 unit from, if you think about college algebra translations. So here we go. He, at 1/4, it is -2, 1/2, -1, 1, 0, 2, 1, 4,
Wait, so are you graphing it?
2, yes. So there he is.
That's
Has a VA,
that's 0.
and he goes out. So his domain is 0 to infinity,
0.
and his range is all real numbers. Yes? If I mark this as my x-axis, this is my y-axis. If I'm doing the inverse function, what do I do?
So that's still the
Flip x and
y.
y, and now who does he look like?
There it goes. Okay.
He looks like the exponential.
There.
But if I flip x and
No, he doesn't.
y, there's your log. 0 to infinity.